Okay, so this video is going to cover the content of 2.1 algorithms. I'm going to focus on the content and I'll do a separate video for past paper questions. Right, so let's have a look at the content. First topic, principles of computational thinking. So the way that you have to think when you are trying to solve a problem before you might program it, for example. There are three terms you need to know the definition for: abstraction, decomposition, algorithmic thinking. The next topic is designing, creating and refining algorithms. So identifying input, process and output for a problem. Structure diagrams, which has never ever come up, but I'll show you what one of those is. Pseudocode, which is when you write your code in kind of like not a real programming language, so you don't have to worry too much about the syntax. And the idea is that you could then use that pseudocode to create the program in any programming language. It's the logic really and the structure rather than focusing upon the actual detail of the programming language. You can represent algorithms of flowcharts. You might have to create a flowchart. You might have to finish a flowchart that they've put in the exam paper. Reference language, high-level programming language. That is just there to say that you should have done some programming, which you all have. Identifying common errors. So the kind of exam question there would be they'd give you an algorithm and get you to identify a syntax or a logic error within that algorithm. Syntax is going to be like missing brackets, missing speech marks. Logic error, likely that it's doing a wrong mathematical operator, something like that. So logic error, the program will still run, it just won't give you the expected outcome. And a trace table is when you trace through an algorithm and you show what's happening to the data inside variables as you go through the algorithm, and also what's outputted. Okay, and the other bit of this topic is the searching and sorting algorithms. You do not need to know the code, remember the code, but you do need to know how they work. You need to know any prerequisites, and you need to be able to apply one of these algorithms to some data that the exam board give you in the exam. You might be given the code and asked to identify the algorithm as well. Alright, so the first topic, computational thinking. Algorithms are a set of instructions that solve a problem, so some code that does something. Abstraction is a computational thinking method. It's where you focus on what's important and ignore unnecessary detail. Decomposition. You break down a problem into smaller chunks which are easier to solve than the whole big problem. Algorithmic thinking. Basically breaking a problem down into steps. You follow those steps to solve the problem. Pseudocode I've already mentioned. Writing your code in pseudocode to represent the algorithm helps avoid mistakes when you actually write the code, and it's easily converted into any programming language. If you have to do a flowchart, you start with one of these shapes. It's kind of oval shape. That's your start-stop shape. Any inputs and outputs, so any inputs and prints, are going to go in this shape here. Parallelogram. Then you've got your rectangle for processes, so things like maths, like x equals x plus 1, something like that, would go in your process shape. This shape you use for loops and ifs. So you could do, if you're doing a for loop, you might do something which says I less than 10, and if that's true, you're going to loop back round. If it's false, you're going to come out of the loop, basically. That's how you would do a for loop. A while loop would be similar. You could do x greater than 100. So while x is greater than 100, it loops, and when it's not, it exits. So you write the kind of condition for the if or the loop in here, and you must have two lines coming off this shape. One needs to say true, one needs to say false. This is a subprogram shape, so it looks like the process shape, but it's got these vertical bars running down the side. So if you're creating a flowchart to represent the main bit of a program, and then there was a subprogram off to the side, that subprogram would also have a start and a stop shape and all of the commands in between. but this would have be in the main program, and this would have the name of the subprogram listed on it, and that would indicate that at that point in the program it goes off and runs the other one. It's never actually come up, that shape. You have to get the right shape, so you do get a mark for the correct shapes. You get a mark for 2 lines coming off this one. You get marks for saying true and false, so don't forget those things. Okay, searching and sorting then. Let me just check that we've covered everything there. Oh, we haven't got a trace table. I think in one of the other videos that I've done, I go through a trace table, so you could go and have a look at that for that one. Alright, so linear search. Linear search, you've got a list or an array of items. It goes through each one by one until it finds a match. That's the code for it. You can pause this video, have a look at it if you want to spend more time on that. Binary search. So these are the 2 search algorithms you need to know. Binary search, what happens is you've got your list of items. They have a position up here. You have your search term, so what you're looking for. Now what it does with a binary search is it goes down the middle, and it compares your search term with what's in the middle, and it will discard the side of the list that it doesn't need. So for example, if we were searching for B, we would discard, it would check whether or not B is greater than or less than the middle point, and discard this side of the list. And it keeps on repeating that until it finds the search term. Okay. That is the algorithm for binary search. Just look for this midpoint if you have to do that. Look at maybe the length of the list divided by 2. That will indicate to you it's a binary search. Typical question. Giving you some data, a list, and then saying, why couldn't you do a binary search on that? Well, the list has to be in order. It has to be sorted. So that's the prerequisite. A prerequisite means something that has to be the case for something to kind of work. Moving down, I'm going to go to the bubble sort. So a bubble sort, what it does is it takes a list of items, like let's say this is the list, and it compares the first 2, and if it needs to swap them, it will swap them. It will then contain this one, so it will compare this one and this one, and it will switch them. And then it will compare this one and this one, and it will switch them if necessary. And that would be the end of the first pass. So in this case, it's going to switch D and A. Let's say it's sorting this list alphabetically. It's going to switch D and A, then it will switch D and C, and then it will switch D and B. Now it's not fully sorted at that point, but at the end of the first pass, what you end up with is the D there. That's the end of the first pass, that one there. The biggest value always bubbles to the right hand side. That's why it's called a bubble sort. Then with this one, the second pass sorts the list because it just switches C and B, and then it's sorted. And then you can program it to stop when no more swaps are made, and that's how it knows to stop. There is an example of it. There are different ways of doing this actually, but look for a check between 2 items, look for that +1 there, and then look for a swap happening, a swap variable, and it will be a bubble sort. Merge sort, it takes a list and then it just breaks them all down into all the items into their own separate lists. Then it starts to compare and put them together in pairs, and then the pairs are put together in 4s. It's more efficient than a bubble sort. It takes the same time for any list regardless of how unordered it is, so you can predict how long it's going to take to actually sort that list. Disadvantages, you could sort a smaller list in a quicker way, and it takes up a lot of memory. Okay, so it breaks down the it's not a very good visual actually. Think of it like this. Yeah, this is better. So it separates them all into 8 one-item lists, then it merges them in pairs, then it merges them again, and then you get your final sorted list. Now insertion sort takes the first item in the list and creates a new list out of it, and then you have one that becomes the sorted list and everything else is the unsorted list. Then it takes the first item of the unsorted list and starts slotting it into the right place in the sorted list. It's fairly easy to code. I wouldn't say it's really easy to code. Bubble sort's easier, but anyway, it's good for small lists, less memory used than a merge sort, and but the disadvantage, inefficient with large lists. That's the same for bubble sort as well. So the way it works is it creates that sorted list out of the first item, and then it takes the next item and slots it into the right place until they're all in the right place. Okay, so that is it for this topic. These other things, I didn't mention structure diagrams. A structure diagram is like a little hierarchy diagram which shows subprograms within a program. So it's kind of like you'd have your main program, that's your main one, and then you might have check name. Let's imagine it's a login thing. So you check the name exists, and let's say then you check the password, and imagine these are sub-programs to this main program. So that one goes to kind of there, and then that one goes to there. And if this sub-program then had other sub-programs within it, they would be on this level of the hierarchy, but that's a structure diagram. Okay, I think we'll finish there.